Yeah, it's streaming, should be streaming at least. Hello, how are you?
Good. Good.
How was the previous lecture with Per Morten? Did you learn like lots of new stuff in C++?
That previous lecture were more introduction to the rapid class.
Well, it's a previous programming.
The previous one, yeah. Yeah, we learned stuff.
Cool. And did everyone complete the first lab? Because tomorrow we're gonna build on something on that, so just want to make sure that everyone's finished with that. The very first lab 2 weeks ago.
Install OpenGL, open up the code that.
And yeah, that simple primitive.
Get the image that was on the PDF.
Yeah, exactly. All right, let's start with today's lecture then. It's mostly about pipeline and very basic introduction to OpenGL. And yeah, one announcement probably you have seen on the wiki. I removed the date of the assignment announcement because it should have been introduced today, but I think it's better to like have this lecture and the lecture after that and then introduce it afterwards, because it will be easier for understanding and to tackle. So let's postpone starting the first assignment just by 1 week. Is it all right for you?
We have other assignments, so it's fine.
Yeah, great. Great, let's start then. Yeah, with start with basic concepts, like anything new to you, like, or does anyone know like primitives? Well, what are the primitives like in OpenGL pipeline and in graphics in general? Yeah.
Points, lines, and triangles.
Yeah, exactly. Yeah. More primitives that are not written here. Can you name any of them?
Quads, but they don't work with them directly, right? Or
Sorry?
Quads, but you don't work with them directly, right?
Yeah, they can be primitives, but yeah, we mostly focus on triangles here. Yeah, any more ideas? Okay, yeah, models are mostly the actual representation of some object in space that we want to render and represent on the scene. Like, and they are composed of primitives, as we already mentioned, like vertices that the corresponding primitive can be a point, just simple point, or line that is connection of points, or polygons, closed surface, or triangles that is a subset of polygons in general. And the scenes are introduction of those ideas and visualization them into 2D or 3D space. So we don't take them in isolation. We have these models in some scene, in some environment and context. And the rendering process, it's probably familiar to all of you, is just the whole sequence of processes when we take this very basic input of models and all other parameters defining the scene and generating the final 2D scene that is displayed on the image, or the image that is displayed on the display scene monitor. Sorry. And graphics pipeline is all steps in this process, like steps towards the conversion models into the visualization, into the displayed image on the monitor. And it can be optionally manipulable. It's not mandatory, but we can, like in modern versions of OpenGL, we can program shaders and we can manipulate them. And to make it simple, it's just like taking models, putting into some world context, consider the eye camera, the observation point, the perspective, and raster it then down to make it pixelized to be compatible with the device, and then put in the frame buffer for visualization. So before starting with more details, I still need your input. Why OpenGL? Why do you think you need this, and why is it a good idea? I want to hear from you. So, what is your inspiration? Yeah?
Understanding how graphics are implemented on a lower level. So, what's behind the scenes in, for example, if you play a game, what it takes to get the rendering on screen.
Yeah, that's a nice point. Anything more? Why particularly OpenGL? Yeah, please.
It's for this course at least, it's relatively cross-platform, so you don't have to spend too much time on doing very specific thing for your operating system.
Yeah,
That's
that's
focus more on the graphics.
yeah, that's a nice advantage of it. Someone from this side wanted to add? Yeah.
I don't know if it's actually the case, but is it relatively easy to get into, maybe? I don't know.
It depends what we are comparing with, but
Compared to other alternatives, is it easier to use?
yeah, we can say that. It's still like very subjective, but yeah, easier to understand when you really start getting into, like, to understand the processes and what's happening and what are the steps and procedures. Okay, before getting to OpenGL, what was timeline, and let's start chronologically. How did we get to modern graphics and OpenGL? So initially it was just like scrolling games that we have seen on the first lecture, when you have just a side view and you have a 2D plane, but there was still created illusion of 3 dimensions. And this was made possible using some tricks, like, for example, copying the vertical scan lines instead of scaling them, because and directly manipulating each area of the background layer, because it was very computationally costly, and then manipulate them afterwards depending on their desired location in the background space. So, for example, here you can see that the lines that are farther are thinner as well, and also cover wider range, and so on. So this makes an illusion of having 3 dimensions. Also, like, because the resolution was not very good at times, like we have blocking artifacts in front. In the front plane. So if you're interested in general in the cues that human visual system uses for depth perception and 3-dimension perception, we can have this included in the lecture when we will talk about human vision, if you're interested. Like exactly what are cues, what are the things our brain interprets as 3-dimensional. But yeah, the general idea was to use these tricks to have impression of 3 dimensions. And yeah, some important points to remember is that the player position in the game world and on the screen should be converted, and we need translation, because game world position and camera position are differ, and we need this translation. Even it can be very simple, just from float to integer, but still some procedures are needed for that. Yeah, the next step was dedicated graphics processing. Several proprietary implementations appeared afterwards, like RenderMan by Pixar Studio, that was made open source version recently, as far as I know. Also, like some APIs that were like NVIDIA specific, and high-level shader language for Microsoft's DirectX. And here is kind of overall structure of influences, historical influences. We have general purpose languages with dash line, we have graphics APIs, and we have shading languages. And as you see here, OpenGL is primarily based on or inspired from or influenced by IrisGL. Yeah, before talking about IrisGL, what does OpenGL do and what it doesn't for us? Yeah, it's you mentioned the two kind of low-level understanding, but it's considered medium-level API, and it's mostly intended for rendering effects, to be high performance, to be independent cross-platform and flexible, and it's pretty stable. Deprecation model was introduced in the third version. So do you know what is deprecation? Some of the functionalities were marked as unnecessary, so from version to version then started to retire or remove some of the OpenGL functionalities becoming obsolete or unnecessary in the modern models. And yeah, it has very particular focused functionality. It doesn't cover networking or sound effects, and as it's medium level API, it doesn't really deal with low level input output interaction, and neither high level functionality like windowing in specific operating systems. Like for windowing, as we have seen on the previous lab, we can use like GLFW, for example, or other implementations. So it's not supported directly by OpenGL. Yeah, to get back to history, it has roots in IrisGL that was proprietary. It did not have very formal and clear specification, and it didn't really went through any conformance tests, so there was need for something more reliable, something more standardized and open source and open for everyone, and that's how OpenGL started back in 1992. But initial version did not really have like as much capabilities as it has today. For example, it did not support any texture mapping. It was introduced only in the subsequent version in 1997. And the general trend is that it is incremental. New extensions and new capabilities are added in further specifications, and usually they try to make it backwards compatible to avoid making older OpenGL implementations still functional and not to make them obsolete. And the first version was a fixed function pipeline, so we could not really program or manipulate it. It was just fixed, whatever was given. In just version 2, they introduced a programmable and manipulable pipeline. In versions 3, they started marking and then removing some obsolete functionalities, like fixed function pipeline was removed in the subsequent version. And yeah, requirements to deal with transformation, texture mapping, etc. also appeared by the time. So it was this OpenGL implementation is product of Chronos Group, which is a non-profit consortium of today more than 120 companies who collaborate on definition of the specification. And they have they don't only deal with OpenGL, but here we have whole range of standards defined by them. In 90s they started with OpenGL, that primary purpose was cross-platform free apps and gaming, and then they introduced in 2000s embedded system OpenGL that was intended for embedded systems like in any machines and also mobile technologies. Safety critical graphics was introduced in 2005. So any idea what safety critical implies in this case? What kind of applications? Like any application that has top priority for safety, because its failure might lead to catastrophic results, like in military or in medicine, where they deal with human life, very high importance applications. And then in 2008 they introduced OpenGL language for parallel computing, and in 2014 intermediate language was introduced for something in between graphics and parallel computing. I will talk about it a bit later. And finally in 2015 they introduced Vulkan, that primarily intended for very high efficiency. And on the right side you can see the news SIGGRAPH reported introduction of all those specifications. So if any of you do not know, SIGGRAPH is one of the primary computer graphics annual conferences held primarily in the North America, and it's one of the most difficult conferences to get into. Yeah, version history, like from 1992 to 2003, we had a fixed pipeline. We could not program our own shaders, and we could not really manipulate whatever was given. But since 2004, we get capability to amend and modify vertex, fragment, or geometry shaders according to our needs. And there are two different profiles: legacy OpenGL profile and core profile. Core profile includes capabilities, just core capabilities that have never been removed or retired, while legacy OpenGL includes all the functionalities that including some of those which were later removed and considered obsolete. So core is functional throughout the whole timeline, while legacy includes already some of the removed capabilities. To have a bird's eye view on the pipeline in 2.0 version. So how OpenGL pipeline looks. We have vertices defining the model, just coordinates in 3D space. We have a vertex shader. I will talk about each step into details on the next slides. And pixel or fragment shader that we can program. So those are the areas where we can really make changes. We have generating primitive steps, so this is just creating triangles or lines or whatever polygons or whatever we want our object to be composed of. Then there is rasterization step, when this model is converted into pixelized representation to get ready for displaying on the monitor. And we shape them, give value to those pixels. There is some post-processing afterwards, and we put to the frame buffer to visualize to the observer. So to go into deeper details, like vertex specification is just definition of the model. What are input vertices? What do we have? What data do we have? Vertex shader is modification of those vertices. It takes one vertex as an input, makes some conversions, and gives output as another vertex. So it's just one-to-one mapping, and mostly it's used for viewpoint transformations and for perspective changes. And then we have vertex post-processing, for example, clipping to leave whatever is within the field of view. Afterwards we have primitive assembly, so like defining drawing order and decomposing our shape into smaller pieces, and definition of the triangles. Rasterization, as I have already said, that produces fragments that are fragments are basis for pixels, but it's not, there is no one-to-one mapping, because some fragments might not be visualized as pixels because there might be occlusion, there might be overlay by another layer or another fragment, but it's the basis that it's kind of raw data ready for visualization as pixels. Then we have shader that is either default, or we can optionally program it and depend how to shade and how to define our fragments, and it assigns particular color to all fragments. So this is actual visual appearance. While we had just geometric definition till now, from this point we already have something visual and tangible. And finally, again, post-processing before putting to the screen, like this can be moving redundant vertices, duplicate vertices and points like this, just final refinement. However, in model, in the next version 3.0, there was added geometry shader, an optional layer that gave additional tools to the programmers using. Yeah, well, first of all, deprecation model was introduced, and this was one of the major aspects of this model. But geometry shader give additional capabilities to the programmers, like till now it was possible to create just predefined primitives, while using geometry shader we can have any arbitrary primitives we want, and for example in this case we have 3 vertices, and like very simple intuitive primitive is triangle. However, using geometry shader, if we program it accordingly, we have like primitive different from that, like this kind of offset triangle. So it's just manipulating primitives according to our taste and needs. And in the 4th version there was another optional layer introduced, tessellation. That is also optional, so we can just skip it and it will work like by default values. However, we have additional capability to control how this surface is defined. So tessellation does, yeah, here is kind of definition, but can anyone explain more in more understandable way? How do you understand that word? What is tessellation? Any ideas? Yeah?
Like repeated subdivision of a surface into sort of more triangles and finer detail. So like this table could be 2 triangles, or it could be and then processed and subdivided to get more and more detail on the table, for example.
Yeah, that's very nice. Yeah, nice explanation. Yeah, subdividing into smaller patches, into smaller pieces, to imagine a mosaic when it's split into smaller tiles of mosaic. And what are the 2 important conditions to be fulfilled in this tessellation process? So when you have the surface and want to split into smaller pieces, what conditions should you fulfill? So it's important to not to have gaps or space between the smaller patches to cover the whole surface, and also not to have overlap among the tiles, so to have each particular area defined just by one particular primitive or subdivision object. Yeah, and tessellation has 3 components: tessellation control shader, or TCS, which is just subdivision algorithm. How should we subdivide our space into smaller pieces. So how this should be done mathematically, and this step is very important when we have two surfaces with two different tessellations, because algorithm should make sure that the borders are smooth, and due to different tessellation approaches we don't have any gaps or any breaks or overlaps. Afterwards we have a primitive generator that actually is based on TCS. It takes input from TCS and actually carries out this tessellation process, splitting into smaller primitives or other arrangement of primitives. And finally we have tessellation evaluation shader, which computes new information for each new generated vertex. Yeah, so here are the examples. Like upper one is just splitting this patch into some pieces, and here we have different levels of inner tessellation. So initially we had 3 points defining the triangle, and afterwards we had 1 point between each of them, and then appeared 2 points on the third level, and so on. And as we see, the number of vertices and number of sub parts or subdivisions increases as we make it further subdivided. Yeah, to have more into details into overall OpenGL 4.5 version. So as we already mentioned, we have vertex specification, vertex shading, then tessellation, geometry shading that is manipulated by us, rasterization process, fragment shading, and frame buffer. But here are several important points to mention. First of all, fragment shading, as you see here, is geometry shading. I'm sorry, geometry shading, as you see here, gives us transform feedback that is then returned in the buffer. So, any ideas? Any guesses what is transform buffer? The idea is that when we have defined geometry, we pass it to GPU for further processing. But particular geometry can be useful for future uses, maybe in future frames, or we want to store it somewhere. Because otherwise, if we define the geometry, then pass it from CPU to GPU, and we want to use it again, we have to rewrite it back, and this takes too much computation and unnecessary overhead. So this is just storing geometry for further use in the general memory before passing to the graphics card. And yeah, I will transfer. Yeah, and it's written in the buffer. Another interesting point here is that vertex processing and rasterization is removed from. So it's here. Vertex processing and rasterization is removed from CPU load and are passed to GPU for processing. And also in OpenGL 4 we have better texture sampling and texture processing capabilities that are fed into vertex specification and further processing steps. And in version 4.6, that is the next version, we have that SPIR intermediate language to make it possible to write simpler to write simpler shaders in different languages and to make it more portable for us, rather than writing it in pretty complicated GL, SL language, like shader language. And for any details like how OpenGL was involved and what were actual features and capabilities of each of those OpenGL versions, you can refer to Kronos website. Here is a reference. By the way, I have uploaded this to Wiki, so you can download the slides already. Let's continue with actual programming part. So we are gonna now talk about language, the language concepts. What are the data types in OpenGL? What are the basic functions? Also more details about primitives and shaders, but we will go into deeper details on in the next lectures. Well, vertex is just location in space, just a 3D coordinate that can have some attributes like color or texture coordinates. It's coordinate within some particular texture, and it's given in 4-dimensional vector representation, and given like by 4 x, y, z, w coordinates. And any idea, if we have 3D space, why do we need 4 coordinates? What are, yeah?
To allow for transformation with matrices.
Yeah.
Do you need the 4th coordinate to do translations?
Yeah, exactly. So 4 coordinate enables simpler and smoother matrix manipulations, and it's called homogeneous coordinate, and that is also used for normalization. Usually w is equal to 1, but if we change the value of w, it means division of x, y, z by this number, and we make some normalization or manipulation of this one. And there was one very interesting example I was reading on the internet, usage of this w in 2D plane. When you have 2 parallel lines, they never converge, they never overlap, but the w is used for perspective definition, because when we have 2 parallel lines and it's going farther in space, at some point they are not differentiable. So if we put w to 0, the coordinates will overlap in infinity. And vertices are stored in vertex buffer objects, and VBOs are or vertex buffer objects are referenced by vertex array objects that are actual organization and description of whatever data is in vertex buffer objects. So to have a parallel like VAO, vertex array object, is like a program, for example Microsoft Word, that has some protocols how to read the data, while a VBO, vertex buffer object, is actual text like typed by us and stored in docx object. So VBO stores actual numbers like vertex coordinates, like coordinate in the space, while VBA has information how this data should be read and interpreted and understood. Here are the data types in OpenGL. As we work with C++, it's possible to parse them into simple C++ data types, but still we can like simply stick to those data types. I think none of them are unfamiliar to you, like simple byte, unsigned byte, short, that ranges to -32,000 to +32,000, unsigned one, integer, floating point ones. And one rule of thumb is that just use the smallest smallest data type you need for a particular variable and application to just decrease overhead and complexity. Yeah, this is deprecated, already obsolete way of defining vertices. So if you see anywhere in the tutorial this kind of definition, this means that you're dealing with old version that is not really used in the modern version. So what's happening here is that we just define the list, then we start here with begin, and we start entering the vertices of the triangles, and then we define each vertex separately, like three floating points for 3 vertices. Then we have end function, we end the list, and if we want to refer to them somewhere, we just call this particular list defined up there. However, in 4.5 we do that in a different way that we see later. And what are the pipeline principles? So it has a can be taken actually as a state machine. So any idea what is a state machine? Yeah, please.
A huge collection of data, and that can be changed from, like, by transitioning states or calling functions into it. But it's like
yes.
states that can transition as well in another sense.
Yeah, it has states from some finite number of possible states, and at one particular point in time it has one particular state, and it depends on external inputs and manipulations to switch from one state to another state. So in this case, external input or manipulation is whatever we, for example, program and provide as a shader. And yeah, there is predefined pipeline, but in comparison with a fixed pipeline implementation, we can provide some input and configure it according to our needs. And pipeline has sequential execution, which means that output of one stage is used as an input to the subsequent stage. However, it might have side effects. This means that a change on one of the layers can impact other parts of the pipeline at some point. And yeah, and as I've mentioned, like we some stage produces output, and then it's taken as an input for later stages, and this process is continuous until we end up displaying the rendered image on the screen. So double buffering, can anyone say what it is and why is it important? Yeah?
Well, you have in OpenGL this is something called double buffering, I think. So instead of rendering to, and you think about it as having two different images in a way. And you have an image displayed on the screen that you can see, and then you render the next frame onto like an image that's kind of in the back. And when that image is full, you know, you can just swap. So you can get really, it looks a lot better when you use double buffering. Because if you don't, it would just like fill up the
yeah.
frame from this, and it will flicker.
Yeah, exactly. Exactly.
It looks better, and it allows to get more out of your GPU. Because you can render to the next frame.
Yeah, exactly.
You can do triple buffering and
yeah, so as you mentioned, like tearing, so having pixels or fragments present from 2 different frames, that is like very obvious artifact you have seen maybe in the television when you have transition from frame to frame. You still have some areas visible from the previous frame. You have something from the new frame, and it does not really make much sense, and it looks very ugly. So to avoid this, or like stuttering in transition or any other visual artifacts, we need double buffers. So it's not really reliable to write directly into actual whatever is displayed. So we have something, as we have already mentioned, some buffer in the background. While one frame is presented, the new rendered frame is written into this background buffer, and as soon as it's ready, then it's flipped. However, this has another advantage. It gives us possibility to control frame rate, so we can decide when to swap, and we can control frame rate according to our needs. Is the advantage of double buffering clear to everyone? Why we need the second buffer in the background? Or any doubts? Anyone not really sure? Okay, then who can tell me why do we need then triple buffering? Why to introduce extra buffer in the background? Okay.
Try there, but since you can kind of have if you're done with the two buffers, then you can start blending the third buffer, and so you can use your GPU, so it's not just being idle and not doing anything. So it has something more to work on. So it's a bit more, you get a bit more performance out of your hardware, because you can render more, because there's more work to be done ready for you. I'm not. Yeah, I don't think it's advantage to go over triple buffering. I don't think that has much effects.
Yeah, that's one point, and that's important. If you're done with the second buffer writing in the background, you don't need your system to be idle. But there is another significant advantage, another way of saving resources and just using time as effectively as possible. Anybody? So when you can't write anything, when you have two buffers, when you have like double buffer, one foreground and one background buffer, back buffer, so at which point is your system idle? Except for when you're already writing one frame, rendering one frame. Yeah?
When both are full and you're waiting to swap.
Yeah, exactly. When you're swapping them, in the process of swapping, your machine is idle because you're swapping the two buffers, and in the meantime you can actually start rendering the third one and writing in the third buffer. Yeah, that's just saving time that is used for swapping. Yeah, it was actually written here, and you don't need to wait for swapping. Yeah, before we start with actual usage of the pipeline, I propose to have a short break. Is it okay for you? And then we can start with actual implementation and yeah, 10-15 minutes.
You make the call, just tell them when you want the break.
Yeah, let's be back at 1/4 latest 1/4.
Cool.
So watch this.
Oh, cool. Okay, I sent